Hello, are the slides visible and am I audible to you?
Yes.
Okay. Okay, we'll wait for I think 2 more minutes so that some more people can join and then we will start the class. Yeah, hello, good evening everyone. So let's start the class now. I think not many people will join. So anyway, so welcome to the NPTEL online course on water and wastewater treatment. So we'll be having the problem solving and doubt clarification session now for week 6 contents. And as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So let us quickly see the contents of week 6. So we started with the phosphorus removal, basically the biological phosphorus removal process, and then we also looked into the chemical precipitation thing. And we also learned about the secondary clarifiers and different types of attached growth systems like the trickling filter, rotatory biological contactors, and the moving bed biofilm reactor. So moving bed diaphragm reactor is nothing but an uh, modification of ASP. Okay, and then we looked into some disinfection systems. So what is the basic kinetics of a chemical disinfection system, and what are the different components and methods? And in those methods, we learned about chlorination. Okay, what are the various redox reactions involved in chlorination, and how does the chlorine gas, hypochlorite, or chloramines are formed in this system? And after that we learned about the disinfection byproducts, okay, which are formed during various kinds of chlorination processes. And at last we learned about the chlorination breakthrough curve, which is very important for these concepts, and we will also solve some problems in this particular thing. And at last we learned about the ozonation and UV disinfection. So this was the brief overview of the uh, lecture contents. So now we'll be solving some MCQ problems, and yeah, mostly theoretical and some numerical also. So let's start with the first problem. It says that select the correct option about phosphorus removal. So phosphate consumed by bacteria in aerobic zone. Bacteria forms PHBs by fermentation byproducts in anaerobic zone. Polyphosphates break down and orthophosphates are released in the anaerobic zone, and all of the above. So which of the option do you think is correct? So you can mark the correct option in the chat box. So what do you think is the correct option? Because as you all know, this question is about the biological phosphorus removal technique. So we have the anaerobic zone, we have the aerobic zone. So there are many processes going on simultaneously. So some of them are written. Find out whether these statements are true or false, and which of them are correct. So what do you think is the right answer? Any idea regarding this? So we are talking about the biological phosphorus removal. Biological, not the chemical precipitation thing. 1D. Okay. Any other answer? So you think that all the statements are true. Okay. So first of all, why do we need phosphorus removal? Why is it so important? Any idea? Why do you want to remove the phosphorus from the system? What is the problem?
It causes eutrophication of lakes.
Yes.
It's a nutrient.
Yes, it's one of the major nutrient. Okay, so nitrogen and phosphorus, two major nutrients, where phosphorus is the basically the limiting nutrient. Okay, so even in small quantity, if it is present, it can cause high amounts of eutrophication or algal blooms that we generally see in any kind of lake or something. So just a second. Yeah. So let's discuss about it. Okay, because I think this is one of the important aspect of this. So we will come back to the question anyway, but before that, let me give a brief idea about what is going on, because there are many processes are involved. So what are these organisms called which contribute to the phosphorus removal? Any idea what are these organisms called?
Phosphate accumulating organisms.
Yes, phosphorus accumulating or phosphate. So we will call it as PAO, phosphate accumulating organisms. So uh, these these organisms take up this phosphorus for their growth. Okay, for as a nutrient they take them up, and they take more than required. Okay, so this is something known as luxury uptake. Okay, so this term is very important, luxury update. So whatever is the requirement, they will take up more than that. So in that process, more and more phosphorus can be removed from the system. So basically, it's uh, it's a system where we have two zones. So first first is the anaerobic or aerobic. Any idea? Which is the first zone? Is it anaerobic or aerobic?
Anaerobic.
Anaerobic, yeah. So first is the anaerobic zone. Okay, that means there is no oxygen, no nitrate, no sulfate, nothing. Okay, it's not anoxic, it's not aerobic, it's anaerobic. And then we have the aerobic zone. Okay, so the actual uptake happens here. The actual uptake happens here, but before that, some things have to be done. So what happens in, so this is maybe zone one, we can say, and this is zone two. So what happens in zone one is that this PAO, okay, okay, these will take up the biodegradable carbon, or I should say, readily biodegradable carbon, which is uh, easier to decompose and take up. Okay, and these are like in the form of VFAs, or we can say them as volatile fatty acids. Okay, so they take up these things. Okay, and these VFAs are converted in their own cells. Okay, they are converted to into something called as PHA, that is polyhydroxy alkanoate. Okay, alkanoate. So these PAO will take up this readily biodegradable carbon, maybe in the form of VFAs. Okay, those are nothing but volatile fatty acids. So these are already present in the system, and they convert into something called as PHA. Okay, so this is something like some energy storage unit. Okay, so they will take them in their body itself, and while they are doing this, so they need some energy, right? They need some energy to do these things. So this energy, the energy that is required for this is derived by breaking down their own intracellular whatever, because some of the polyphosphates are already present in the microorganisms, so they will break down those polyphosphates from their cells. Okay, and to get the energy to store these phas. Okay, why this pH is important we will see in the next unit. So what happens, PAO, they take up the carbon, form this PHA, and this PHA, the energy that is required to form this PHA are obtained by breaking down these polyphosphates within their cells. So in this way, what happens? This polyphosphates or this P is released in the system. Is released in the system. Okay. So instead of taking the phosphorus in the first unit, what is happening? Phosphate is getting released in the system. Okay. Now comes the second unit. Which is an aerobic chamber. So in this, now again, this phosphorus accumulate bacteria will oxidize those pHs. So whatever pHs that were formed, okay, so those pHs will be oxidized and energy will be generated. So energy will be generated. As I told you, these are like energy units. So energy will be generated, and with this energy, the phosphate will be taken up. The phosphate will be again taken up. Okay, so this uptake of this phosphate again will be more than what is required. Okay, more than what is required. So that is why this is called as a luxury uptake. So luxurious life, as the word suggests, luxurious. The what is required more than if we consume, we call it as luxury. So that's why this is called as luxury uptake. This is all clear to all of you? Any doubts in this? Because this is very important, one of the like easily misunderstood things, because in the first chamber phosphate is not taken up by the bacteria, but rather it is released in the system, which is inside their own cell. Then they do the luxury uptake and take up the phosphates more than that is required, and then when we do the secondary clarification or whatever in the secondary clarifier, okay, in the secondary clarifier, with the sludge they are removed. So with the sludge this biomass will go, so with that the phosphate will also be removed. Is it fine? So it is like mostly 80 to 95% efficiency is there, and the effluent phosphate generally will be less than 1 milligram per liter is possible. Okay, and if there is some polishing in the end, some more uptake is there, then less than zero point 0.1 milligram per liter is also possible. So this is highly effective but time taking and like that. Okay, whereas the chemical precipitation will produce a lot of phosphorus containing sludge. So this is the gist of it. So I hope you have understood it. If you have any clarifications, you can ask me right now. So two chambers, both the work you should, the mechanism you should know what is going on. So in that way, all the options that are marked here are correct, because phosphate consumed by bacteria in aerobic zone. Okay, then this bacteria will form this PHB or PHA. Okay, in the anaerobic zone, right? And then the polyphosphates are broken down and orthophosphates are released in the anaerobic zone. So this is the intracellular polyphosphate that we are talking about, right? So all of them are correct. Let's see the next question. So it says that which of the following pair is not correctly matched? Trickling filter to attached growth process, activated sludge process to suspended growth, MBBR to less surface area to grow bacteria, or or secondary disinfection to inactivation of pathogens. So any other answer? Okay. So most of you are answering it as B. Oh, sorry, C. So C is nothing but the MBBR or moving bed biofilm reactor. So the entire idea behind making such a system was to increase the surface area for the bacteria to grow. Okay, we added some plastic media or some extra materials in the system so that we can give some attached growth. Okay, whereas it will be in suspension. So this media is in suspension, whereas the bacteria have some place to get attached to, and we provide more surface area in that way. So that's why option C is not correctly matched. Next problem, let's see. Which of the following form of chlorine disinfectant requires highest contact time to inactivate 99% of bacteria? So is it NH4Cl, OCl minus, HOCl? So which disinfectant will require the highest amount of time?
CHOCl.
So here we are talking about the highest contact time. So if we are giving more contact time, that means it is less effective. Okay, it is less effective than the others. So in that way, we have to answer. So I got one answer as A. So that is the right answer. So this chloramine is the one which is the least effective and will require the highest amount of contact time. Okay, so that's why I mean, whereas the most effective among these is the HOCl. It is the most effective, and under a certain pH range only it will be active. So we have to maintain that kind of pH to get the disinfection power of HOCl. Next, identify the wrong statements. In disk filtration, aeration is controlled by rotation of disk. Na2SO3, okay, removes free chlorine from the treated water. Disinfection byproducts also form in drinking water. Presence of high concentration of H2S and Fe2 plus will increase the residual chlorine in the treated wastewater. So which of them are wrong? Okay, D. Any other answer? Any other wrong statement here? So why do you think the in drinking water there will be no disinfection byproducts?
Because there is no organic matter.
Yes, yes, that is true. So mostly we will. So this statement like also form in drinking water. So we should know the composition of drinking water, right? So if we are not perfectly sure about the composition of drinking water, then we cannot answer this question directly. But mostly in drinking water, organic matters will not be there. So that's why in that aspect, this is a false statement. Okay. And whereas in option D, so H2S and Fe2 plus will decrease the residual chlorine. So even same goes with the Na2SO3. So what happens is, so if Na2SO3, so this is question number 4. So what happens is if Na2SO3 is present and some chlorine is also present in water, so that will form these products. Okay, so this will neutralize the effect of the chlorine, and lesser chlorine will be available for disinfection. Whereas if H2S is present and some Fe2 plus is are present, so these will get oxidized. So H2S will get oxidized to sulfate. Okay, Fe2 plus will get oxidized to Fe3 plus. So these are reducing agents because these are getting oxidized. So because of these things, the effect of chlorine will get decreased. Okay, the lesser amount of chlorine will be available for disinfection. So these are kind of quenchers of chlorine. So ideally in our system, we won't like to have any organic matter or these kind of quenchers, because if organic matters are present, then these disinfection byproducts, trihalomethane, haloacetic acids, all this will be formed. Okay, even some, if some bromine or iodine, these are present, so these will also affect them. So for this question, option C and D are the right options. Yeah, same thing is there. Moving forward, UV disinfection process produces hydroxyl radicals in treated wastewater. Is it true or false? So this is very direct. So mostly it is true because uh, we need some oxidizing agent. Okay, we need some oxidizing agent. So that's why these hydroxyl radicals are very powerful agents, and these are also effective in disinfection. Okay, and even we have we know that by UV radiations we can also do photocatalysis and all these things. So radicals are produced, these hydroxyl radicals are produced in the wastewater. Okay, now a small numerical is there. So it says that the treated wastewater discharge 1,000 m³ per day entering the disinfection unit, and a number of organisms remain after contact time is, some equation is given. Find out the volume of disinfection unit required to achieve 98% efficiency, where K is the disinfection rate constant, which is equal to 0.145 per minute. Okay, so we have to find out the volume of the disinfection unit. Okay, so that it achieves 98% efficiency. And the disinfection equation is also there, or rather the decrease in the number of organisms with time. Okay, that equation is given. So what is the order of the reaction here? Can someone tell me? By seeing the equation, can you tell what is the order of the reaction?
It's a first order reaction.
Yes, yes, this is the first order reaction. So in disinfection, we generally assume that the change in the concentration, okay, follows the first order reaction. Please try to solve it and let me know the right answer. I will wait for 1 or 2 minutes. So can someone tell me how to approach this problem? Uh, Time. Yes, time is correct. Time is correct. 26.97 minutes. Absolutely fine. So now tell me the volume. So volume you should tell me in meter cube. Okay, meter cube should be the unit. Yes, 18.7. That is right. That is right. 7.2 or 7.3, I think. So yeah, it is fine. So for others, let's see how to solve this problem. So question number 6. So first we know that the equation that is given for the number of microorganisms is n naught, nt is equal to n naught e to the power minus kt. Okay, so k here is given as 0.145. So it would become nt is equal to n naught e power minus 0.145 t. So that means at the end of time t, it will follow this kind of curve. So now we know that the disinfection efficiency, okay, something in percent, is nothing but n naught minus nt divided by n naught into 100. Okay, and what is the efficiency given? We have to achieve 98%. So n naught nt we will substitute from the equation n, and then by n naught into 100. So n naught will get cancelled. So ultimately we can get 100, we can bring this side. So 1 minus e power minus 0.145 into t. So if you solve this equation, you will get t something as 26.97 minute. Okay, because this k value is also in minute. So the answer we will get is 26.97 minute. So once you've got the time, so now we have to find out the volume of the, disinfection unit. Okay, so V is equal to discharge into time. V is equal to QT. So Q is 1000 meter cube per day, and time we have 26.97 minutes. So you have to convert this minutes into days. Okay, just convert it and multiply. You will get the final answer as 18.73 meter cube. So many people might stop by solving up to here. They are not asking the time, they are asking the disinfection unit volume. So you have to multiply with the discharge. Okay, I hope this is clear to all of you, right? So one small question, how do we measure the amount of microorganisms present in the system? What is the procedure? How do we measure?
Is it MPN?
Yes. So mostly there are many methods actually. There are plate count methods. There is MPN. So MPN is nothing but most probable number per 100 ml. Like that we measure. So it's a statistical method. Another one method is plate count. Okay, we will try to grow the sample on some nutrient media, agar something, and we will see how many colonies are being formed. So so either you can measure in terms of MPN per 100 ml, or we can measure in terms of CFU per 100 ml. Okay, so CFU is nothing but coliform forming units. Oh, sorry, colony forming units. Okay, colony forming units. So this is plate count, and this is a statistical method, right? So okay, so this is the answer. Next, so here we have a graph which is between the chlorine dose in milligram per liter versus the residual chlorine in milligram per liter. So you have to tell the following which of the options are correct. Okay, this is basically a breakpoint chlorination curve. Okay, so you have to tell me what is the breakpoint chlorine dose, what is the free residual chlorine, what is the combined residual chlorine, what is the total residual chlorine. So please look into this graph and tell me what are the concentrations, or whatever, if whatever it is given it is correct, then let me know what are the correct options, and we will find out if something is incorrect how to calculate that. So I hope everyone is familiar with the breakpoint chlorination curve. If not, I will explain that also, how to get the breakpoint chlorination curve. Anyone who doesn't know about how to calculate this, shall I explain the breakpoint chlorination curve? Yes. Okay. Okay. Let's see what actually is a breakpoint chlorination curve. Why we are bothered about it. Okay. Yeah. So let me draw the curve first. Okay, and then I will explain one by one what is happening. So this is a curve between two things. One is the chlorine added. So how much chlorine we are adding in the system versus the residual chlorine. So what happens is when we add, so first of all, can someone tell me what is the difference between chlorine added and residual chlorine? Because ideally, if we add, suppose some 100 milligram per liter of glucose in my system, okay, 100 milligrams should stay, right? Why there is a concept of residual or anything? What is go happening?
Because chlorine is a strong oxidizing agent, so it will kind of uh, uh, clean this NH3 and organics. So at
Yes.
this break point is the point where this chlorine gets finished, but there should be some extra chlorine added to this solution, so it will kill these pathogens.
Yes. So what happens is, as we saw in one of the problems, that there are many reducing agents. Okay. And there are many organic matter present in the system. So what will happen? They will consume this chlorine, and whatever is required for the disinfection, that dose won't be present in the system. So that's why always what is required for disinfection, we will add more than that. Okay, so that's why we have to know like how much chlorine will be used up by this organic matter or reducing agent or whatever. Okay, so that's why we have to plot a curve like how much chlorine we are adding and how much is actually there for the disinfection. So what happens initially, suppose maybe from, okay, what happened? Yeah, so let's say we're starting from zero. So let's say up to zero point 0.1 milligram per liter or so, whatever chlorine we are adding, there is no residual chlorine. Everything is getting used up. Okay, everything is getting used up. So what is happening to these chlorine is the destruction of chlorine by reducing compound. So suppose some H2S is there or some sulfate, some Fe2 plus is there. So whatever is there, if something of that, those compounds are present, they will directly consume this chlorine and there will be no residual chlorine. So this line will go straight. It will be flat. Or if I mark it with some other color, it will be like this. It will be going flat. Then slowly, if we are adding more and more chlorine, suppose we are adding zero point 0.2, zero point 0.3, zero point 0.4, like that up to some, let's say 0.7. Okay, we are adding more and more chlorine. Slowly, what will happen? There will be some part which will be coming out as residual because uh, some will be remaining without getting used up. Okay, and it will reach some saturation. Okay, so in this area what is happening is the formation of chloroorganic compounds and chloramines. So ideally what should happen if I am adding zero point 0.2 milligram of chlorine, then residual should be also 0.2 milligram, but that won't be the case. Okay, the residual may be zero point 0.1, okay, or point maybe 2. Okay, so maximum, even after adding zero point 0.7 milligram of chlorine, whatever residual is there is only zero point 0.2. So that means zero point 0.5 is getting used up in forming some chloroorganic compounds or some chloramines. Okay, and then whatever these chloramines are getting formed, these will get destructed. Okay, these chloramines and everything will get destructed, and some more residual chlorine will be used up. So there will be a slight downward trend of this residual chlorine. So more and more residual chlorine will be used up. So I will just differentiate this area. So some things will get degraded. So I can write it as destruction of chloramines or some chloroorganic compounds. These will get destructed. Okay. So after the destruction of chloramines and this chloroorganic compounds, now there is no organic matter, nothing is present. Okay, it is free from everything. So now from this point, from this particular point, whatever chlorine we will add, that will come out as residual chlorine. Okay, there will be no destruction, no reduction, nothing, no quenching. So whatever we will add, it will be as it is. So that's why we can see a increase in the residual chlorine like this. Okay, so so if I'm adding zero 0.8, zero 0.9 or like that more and more, so the same amount will be coming out as residual. So what is this angle? How much will be this angle? Any idea? If I'm getting same chlorine added as the residual, what will be the angle?
45.
45. Okay, it will be 45 degree. 45 degree. Because if we see if we see any square, okay, of one unit, always the angle which is forming will be 45 degree. So that's why it will be 45 degree, not some other. Okay, so this is the unit. So this part, this particular part, okay, whatever was remaining after the addition, so this point is called as the breakpoint chlorination, this particular. So maybe this is 0.75. So till we add 0.75 milligram per liter of chlorine, there will be some reduction, destruction, all things will be going on. After this, whatever chlorine we add, it will remain as it is. So this is the break point. Okay. So at the point of breakpoint chlorination, whatever residual is present, that we call it as combined residual, and whatever is present after the breakpoint is known as free residual. Okay, and this is the total. This is the total residual. Is it clear to all of you? Okay, these numbers also are not exactly the actual numbers. It depends on the system, how much organic matter is there, how much uh, reducing compounds are there. So these number will vary. I just given so for some indication. So I hope now it is clear. Okay, so this graph, it can be like this. Okay, it can be like this. Okay, any trends can be there. Okay, trend doesn't matter. It depends on the system. So if you come back to the question now, so here they are giving a simple triangular shaped kind of trend. Okay, but mostly it is not like that. It is not so perfect. Okay, so now tell me, what is the breakpoint chlorine dose? What will be my breakpoint chlorine dose? Look, forget whatever given in the options. What will be my breakpoint chlorine dose?
1.5 mg per liter.
Yes, because at 1.5 mg per liter, the maximum degradation and everything has happened, and even after everything, still 1 point at still there is some zero 0.5 chlorine is still present. So that is the lowest point. So at that point, whatever the chlorine concentration will be there, that will be the breakpoint chlorine dose. So 1.5. Now, what will be the free residual chlorine? Okay, let's before that, what is the combined residual chlorine?
0.5.
So 0.5. So option C is also correct because at the breakpoint dose, okay, whatever the residual chlorine already present, that is the combined residual. Okay, so at the breakpoint chlorine dose, whatever the residual chlorine is present, that will be my combined residual chlorine. Now, what is the free residual chlorine?
More than 0.5.
Yeah, so what is the
1.5. 1.5.
so yes, so that is also 1.5. How it is 1.5? So so you can see here now. So this is zero point 0.5, this one is zero point 0.5. Okay, but till here is the total. So this point denotes the total chlorine residual. So how much is the total residual? Total residual is 2, 2 milligram per liter. Right, it is 2 milligram per liter. So out of 2 milligram per liter, zero point 0.5 is the combined residual chlorine. So the rest of it will be free residual chlorine. That is 1.5. So that is 1.5. And total residual chlorine will be 2 milligram per liter. So in this question, option A and C are correct. Rest of them are wrong. So, so here you can see. So if I make the plot again, so free residual chlorine, either you take this length, okay, either you take this length or you can even take this length. So both will give you the, because since it's a 45-degree angle, so both of them will be correct. Okay, you can take either of the length. So here also, yeah, yeah, this length also you can take. So this is also 3 minus 1.5, it is 1.5. Okay, so 1 and C are correct. A and C are correct. Moving to the next problem now. I hope this is clear to all of you. Yeah, so this is the overall diagram of the breakpoint chlorination curve. Next, select the following advantages of ozone treatment. So what are the advantages? No harmful disinfection byproducts, improves the taste and odor, cheaper than chlorination, requires less contact time, more disinfecting residual power. So which of the following are the advantages?
Require less contact time.
Okay, any other?
More disinfection resident power.
Does ozone have any residual power? Here we are talking about the residual power, not the disinfecting power. Yes, the disinfection power will be more, okay, of ozone, but it doesn't have any residual power. So residual power generally comes with chloramines or something else. Okay, so chlorination only gives some residual power, but ozonation will not give any residual power to the system. So by residual power, I mean that if some contamination happens during the uh, transmission through the pipelines and all, it will be taken care of. So that is the residual power. So yes, A is correct because there is no harmful disinfection byproducts, okay, in ozone. Then there it improves the taste and odor. That is another thing, okay, because again no harmful disinfection. Then it is not cheaper than chlorination. Chlorination is much cheaper because just we have to add one chemical. Then it requires less contact time. That is also true because it is the disinfection power is more. So if power is more, then contact time will be less for the same amount of disinfection. Then it doesn't have a disinfecting power, sorry, residual power. So option A, B and D are correct. Next problem, which of the following is not an advantage of biological phosphorus removal over chemical precipitation? Low chemical consumption, low sludge production, high phosphorus removal efficiency, high chemical consumption. Which of them is not a disadvantage of biological phosphorus removal over chemical? So you be careful with the words that they are using. So they are asking which of them is not a disadvantage. No, not an advantage. Not an advantage.
Sir, it is D, high chemical
Yes.
consumption.
Yes. Yes. So that is D. Okay. So ultimately they are asking what is the disadvantage of the chemical precipitation method. That is the question here. So it is high chemical consumption. Next, the steps for breakpoint chlorination are given below. Select the correct sequence. So destruction of chloramines and chloroorganic compounds, formation of chloroorganic compounds and chloramines, destruction of chlorine by readily reducing compounds, and formation of free chlorine. So which of them is correct? So we discussed in depth regarding this sequence. So please tell me the right answer. So B is the correct answer because this is very direct. So first, the destruction of chlorine by readily reducing compounds will happen. Then the formation of chloroorganic compounds and chloramine will happen. Then the destruction of chloramines and chloroorganic compounds will happen. And then whatever we add, it will be coming out as free chlorine. Okay. So again, the same graph. The mechanism of UV disinfection is that it disinfects by directly damaging the nucleic acid of the pathogens. So is it true or false? So yes, it's true because what happens is it will produce some radicals, okay, and they will directly damage the nucleic acid of the pathogens. Okay, they will cause the cell lysis, increase the permeability of the cell membrane, and then damage the nucleic acid. So it is true. What is the main purpose of using chloramines in water treatment? To remove iron, manganese, to provide a longer lasting residual disinfectant, to to remove phosphorus, to remove sulfur, to remove bacteria and viruses. What
To
is the
remove to remove bacteria and virus.
uh, yeah, that is true. Ultimately, it will give some residual power, but the main purpose of these chloramines are to provide a longer lasting residual disinfectant because the primary job of removing the bacteria and virus is being done by HOCl or OCl. Okay, the main high disinfection power compounds. Okay, so HOCl or OCl minus will only take care of the majority of the disinfection. But if there is some residual power is required for my system so that it can take care of the contamination that can happen during the transmission through pipes, okay, or some other stages, then the chloramines are important because apart from chloramines, uh, any other thing will not work there. Okay, we cannot put everywhere ozone or UV disinfection again and again, okay, or chlorination do again and again. But this chloramines can give some longer lasting residual disinfection. That is the main purpose. Though ultimate purpose is to remove bacteria and virus, but the main purpose for these chloramines is to give a longer lasting residual disinfection. So option B is correct. Select the correct option regarding advantages of trickling filter. A TF can withstand shock loadings. Nitrogen removal efficiency is very high. There is no odor or fly nuisance or simpler operation, which is the advantage of trickling filter. So obviously A is right because trickling filter are known to withstand the shock loadings unlike the other systems. Okay, there is an attached growth system there. Also, nitrogen removal efficiency is not high, okay, in trickling filter because we don't have those selector zones and all. Then there will be a lot of order and fly nuisance. Why? Because it's an attached growth system. The microbes will be growing on the media. Okay, so it will attract a lot of flies. Okay, and it is a simple operation. It is like a filter. So wastewater is trickled down a filter media. So the operation is pretty simple. So that's why option A and D both are correct. Which is the correct sequence of formation of the following compounds during chlorination of water in which ammonia is present? So ammonia means NH3. Okay. So suppose we are adding chlorine and ammonia is present. What is the sequence of the compounds that will be formed? So by sequence, I mean like the best way to visualize is we have ammonia, we are adding some chlorine. So first what will happen? So ammonia is NH3. Okay, so instead of NH3, one of the hydrogen will be removed and one Cl will add. So NH2Cl will first form. Then this NH2Cl will again add with Cl2. Then again NH, instead of one more hydrogen, one hydrogen will be removed and 2Cl will come. Okay. Then again this NHCl2 will combine with chlorine. Then the other hydrogen will also will get removed and another chlorine will be formed. Okay, so this is the order. So 1, 2, 3.
B is the answer.
Yeah, B is the right answer. Which of the following is not an attached growth process? Tricking filter, MBBR, SBR, RBC, ASP. So you should know the full form of all these reactors. So which of them is not an attached growth process?
Trickling filter.
Now here we are talking about attached growth. We just discussed that attached trickling filter is an attached growth because we have a media on which the biomass grows. C and E. Okay. So C is the sequential batch reactor, which is nothing but a kind of modification of ASP. Okay, so instead of doing in separate reactors as ASP, we do everything in the single reactor. So SBR. So both SBR and ASP, they are suspended growth process. Okay, because there is no media for biomass to grow on, whereas trickling filter we have a media. MBBR we add some plastic media for the microbes to grow because it's a moving bed biofilm reactor. And RBC we have rotatory biological contractors. Okay, so we have this kind of system on which the biomass grows. So option C and E are correct. Select the correct statements regarding disinfection and its methods. So we have four statements here. Ozone forms residuals in the disinfection process. The disinfection efficiency of chlorine decreases by increases the contact time. Turbidity affects UV removal efficiency. Ozone requires relatively shorter contact time than chlorination. Please give the right answer.
Sir, A, B, and D.
Okay, so coming to the first question, uh, ozone forms residuals in disinfection process. So generally, ozone will not form any residual in the disinfection process. Okay, so we have seen only chloramines will form residual in disinfection process. It will give a long lasting effect, but not ozone. Okay. Next statement, disinfection efficiency of chlorine decreases by increasing the contact time. So always remember, more the contact time, more will be the efficiency. Okay. But if we want to have the same efficiency for a higher disinfecting power compound, then we provide for lesser time. So those both statements are different. Okay. So more time of contact if we give, definitely the disinfection power will be more. But if we have two compounds, one is having higher disinfection power than the other, okay, power I am saying, than the other, then if I give the higher powered one compound lesser amount of time also, the disinfection efficiency will be the same. Okay, so there is a difference between the two. So that's why option B is also false. So efficiency of chlorine will increase by increasing the time of contact. Okay. Then turbidity affects UV removal efficiency. Obviously, any organic matter, any suspended particle, if it is there, it will cause turbidity and it will affect the UV removal efficiency. Then again, ozone requires relatively shorter contact than chlorination. So here we are saying that ozone is a higher disinfectant, like it is having a higher disinfection power than the chlorine. Okay, so that's why shorter contact time is required for the same efficiency. So here the hidden message is, for the same efficiency we require shorter contact time. Okay, so I hope it is clear. So when you see the time of contact, you have to see whether you are comparing two compounds or we are comparing one compound with more time. So that's how you have to answer. So C and D are correct. I hope this is clear. Any doubts? Because many of you were answering it as B. So B is not right. Okay, another similar problem like the one we did before. So please solve this. So we have a disinfectant solution is used to inactivate a certain microorganism with an initial concentration of 2 into 10 to the 7 CFU per ml. The inactivation rate constant K is 0.03 per hour. How long will it take to reduce the concentration to 0.5 into 10 to the 5 CFU per ml? So here the concentration is in CFU per ml, like the colony forming units. So here the equation is not given, but I think you are aware of the equation. So same equation is used whenever we solve this kind of problem. That is known as the Chick's law. Okay, Chick's law, first order degradation. So please quickly solve this because I don't think much time is required. No idea? So same, yes, 207 is right. Yes. So same Chick's law we will use. So that is Nt is equal to N naught into e to power minus Kt. Okay. So here Nt is 0.5 into 10 to the power 5. N naught is 2.5 into 10 to the power 7. And we have e to the power k is 0.03 per hour into time. So whatever time we will get will be in hours. So 207.15 hours. Very easy. So this equation you will use until unless some other equation is given, they have to use for disinfection these kind of this Chick's law only. Okay. Okay. Now this question is little different. So it says that the pH of a solution after adding acid.
Um,
Okay. It is denoted by HA. Yes, Preeti.
um, is 207 hours a bit too high?
Yes, because here the K is very low, I think. 0.03 per hour. If you see the previous problem the K was 0.145 per minute. Okay. So, but here it is 0.03 per hour. So maybe because
Yeah.
of that, the T value is very high.
Okay.
Okay, depends on the disinfection uh, power of the compound. So yeah, ideally we won't use something like this if it is so high. Okay. Okay, coming back to this problem, the pH of a solution after adding acid is 4.8. So the pKa value is given for the acid. Okay, that is nothing but the dissociation constant. If the concentration of the deprotonated form, that is A minus, is 10 raised to power minus 3.2, then the total concentration of acid at equilibrium is. Yes, Preeti. You are saying anything else?
Oh, no, that's
Oh,
it.
okay.
Thank you.
Any idea about how to solve this problem? Anyone knows?
There's a Hazen formula, like pH equals to pK
Yes,
plus
yes.
log of
Yeah,
A
that
into
is
H.
Henderson Hasselbalch. Henderson
And
Hasselbalch equation. Yes.
yeah,
Yeah. Please substitute the values and get me the answer. So generally any acid we will denote it as HA. So acids are proton donors. Okay. So that's why HA. So it will get separated as H plus A minus. Okay, so H plus and A minus, that by the deprotonated form, it is shown as A minus. As she correctly mentioned, so we have something called as Henderson Hasselbalch equation. Okay, so that is pH is equal to pK plus log A minus by HA. Okay, so concentration of, so pH is given, pK is also given, everything is given. So pH is 4.8 is equal to 3.86 plus log A minus concentration is given. So that is 10 raised to power minus 3.2 divided by what is the HA concentration. So if you solve this, HA concentration will be 7.244 into 10 to the power minus 5 molar. Okay. So like this, you have to solve this, right? So in the answer, they have already mentioned 10 to the power minus 5. So you have to only report 7.244. Okay, you don't have to write the whole thing. You have to see in the answer, it is already mentioned into 10 to the power minus 5. So you have to answer 7.244. Okay. In a trickling filter system, the biomass at the interface of biofilm and the media surface undergoes. So what will happen? So biomass at the interface of biofilm and the media surface, what will happen? So are you able to visualize what are they asking? Any doubt with this question? What are they asking? So suppose we have a trickling filter. Okay, we have some media like this. So I'm just making a cuboid for easy representation. We have a media like this. So what will happen? The biomass will grow over the surface, right? Everywhere the biomass will grow. Okay, slowly the biomass will grow. Now let me say take a cross section. So suppose this is my media. Okay, this is my media. Over this, the biomass is growing. This is the biomass, right? Yeah, this is the biomass that is growing. So first layer of biomass has grown, then next layer has grown. Slowly it will get more thicker and thicker. So what will happen after a point of time, due to the increase in the biomass over the media, this particular section, okay, this inside section which is in contact with the media, okay, with the media will not get oxygen. Okay, the oxygen will not be able to penetrate much. Maybe up to some extent it will penetrate, but not, it might not reach till the surface of this media. So because of this, here the conditions that will be developed will be anaerobic. Okay, so oxygen will not be able to pass through and it will become anaerobic. So now the biomass here in this zone will not be getting oxygen. Okay, slowly the nutrients will dry up. Okay, so after a particular point of time, they will go to endogenous phase. They will feed onto themselves. They will go to the endogenous phase, and then this thing will get cut off and it will be sloughed off from the media. And then again new biomass will grow. So at that point only they are asking. So that's why the biomass at the interface of the biofilm will be having anaerobic condition and endogenous respiration. I hope you understood. Okay, as more and more biomass will grow, the penetration of oxygen will not be there. They will not be getting the nutrients. The biomass will go into the endogenous phase because the food will get over. They will not get the organic matter. So they will enter into endogenous phase and it will be sloughed off later. So option B is correct. So this we have seen. Okay, which of the following is not used for phosphorus removal using chemical precipitation? Which of them is not used? Caustic soda, because lime, ferric chloride, alum, everything we generally use for the removal as a chemical precipitant. Okay, so okay, for changing the concentration of disinfectant, the disinfecting efficiency is expressed by, so disinfection efficiency is expressed in terms of concentration to some power and the time. Okay, so what is the relation between them? And it is always a constant. So is it multiply or divide or to the power of t or to the power of what? So A is the correct answer. So here you can see, so c to the power n into t is a constant. So if we are providing low concentration, then we have to give more time for the constant to be the same. If we are providing less time, then we have to give more concentration. So either way, we have to maintain a constant. So c to the power n into t is a constant. Okay. So this also we have seen, I think. No need. Biological phosphorus removal also we have seen. Yeah. So this question we can solve. Find out the pH of the system when HOCl dissociates at equilibrium, considering HOCl as 9.52 into 10 to the power minus 6 moles per liter and pK as 7.54. So generally any acid I told you we can express as HA. So here it is HOCl. How to do it? Please try, because we have solved a similar problem. So not exactly the same formula we will use, but the same concept we will use. So pK value is already given. pK value is already given. So what is Ka? What is K or pK? It is a dissociation constant, right? K is the dissociation constant. So how do we represent it generally? Dissociation constant. Okay, let me solve this problem. You may try the other problem. Okay, so let's see. So as I told, if you have any acid HA, it can dissociate as H plus A minus. Okay, so in this case it is HOCl, so it will be H plus OCl minus. So this is how it's. So now Ka, what is Ka dissociation constant? It is nothing but the concentration of H plus, or the product of the concentration of the products divided by the concentration of the reactant. So that's how we define the Ka. Yes, you are trying to say something? Okay. So that's how we define the Ka value. Now we are given pK value. Okay, pK value is nothing but another form of representing Ka. Okay, in terms of like H concentration to pH. So pK also we can convert into Ka. So pK is given as 7.54. So from this we can find K. So K is nothing but 10 raised to power minus pK. Okay, so 10 raised to power minus 7.54. So K will come out to be 2.884 into 10 raised to power minus 8. Okay, so K we got. HOCl is already given in the problem. Okay, HOCl is already given in the problem. So this is also known. This is also known. Now these two, H plus and OCl minus. So here one small assumption that you have to make is it is at equilibrium. So at equilibrium, we will consider that H plus concentration will be equal to OCl minus concentration. This is the small assumption that you have to make, that at equilibrium, H, if nothing is given, we will consider it to be in equilibrium. So H plus will be is equal to my OCl minus. So so this will become H square. So this will be like 2.884 into 10 to the power minus 8 is equal to, I will write it as H plus square divided by HOCl is 9.53 into 10 to the power 6. So from here we will get H plus. So that is 5.24 into 10 to the power minus 7. So from here in our question they have asked the pH. So pH is negative log of H plus. So minus log 6.28. Okay, so that's how you have to do it. Is it clear to all of you? Right, very simple. So first define what is the dissociation constant. That is the product of all the products divided by the product of all the reactants. So here we have only one reactant, that's why HOCl. Then find out the pK. From the pK, calculate the K. HOCl concentration is already given. So mostly this type of question, some parameters will be missing from this equation. We have to calculate the missing one. And if nothing is given about the concentration of H plus and OCl minus, then we will consider it to be in equilibrium so that everything becomes equal. Okay. Okay. So similarly now same problem. Suppose same problem. I am just changing the parameters. So here I am giving it is at neutral pH. Okay. HOCl is 9.53 into 10 to the power minus 6 concentration. Okay. pK is 7.54, same. Now find out what is the OCl minus concentration. So how we will do this? Any idea? Now find out.
OCl total will be equal to concentration of HOCl plus OCl minus concentration.
So no, I am saying just OCl minus you have to find out. Why you are subtracting it?
Oh, okay.
Yeah. Here the only change in the question is it is at neutral pH. That's what they are changing. Rest everything is saying they are asking what is the HOCl. So again you have to use the same equation. So Ka is equal to H plus OCl minus divided by HOCl, right? Ka value is known, HOCl value is known. These two are not known. We have to find OCl minus, right? What is the H plus concentration here?
Because it's in neutral, it's
So what will be the H plus concentration? What is the neutral pH?
7.
7, right? So what will be my H plus concentration? 10 raised to the power minus pH. 10 raised to the power minus 7. Simple. So we will put this here. So all these are known. We have to find out OCl minus. Simply. Right?
Sir,
Okay.
this problem was solved in the class, and
Okay.
sir had a different approach to this. Um,
Like how? What was the approach?
so he was saying that there is a. He was showing the graph, and
Is it
um,
is it exactly the same problem?
I think so. Yeah, also with the same numbers.
Okay.
Yeah, so the Henderson-Hasselbeck equation, he showed the Henderson-Hasselbeck equation,
Okay.
and then he said that the total concentration of OCl will be equal to HOCl plus OCl minus. There was a graph which he showed where, you know, as the OCl increases, the HOCl decreases. There's a graph.
Yeah.
Yeah. So he was saying when the pH it goes to neutral, there'll be changes in HOCl and OCl minus concentration also. So hence,
Okay. So, but actually, in this question, it is uh, I I don't think because those concepts will be required because it is can be directly done with this only. Okay, maybe I will look into that. What was the background of that problem? Maybe something
sure,
is
sir.
different. Okay, I
Yeah,
will go through it and then I will maybe in the next class I can discuss that. Okay,
sure, sir.
so let me see that
Thank you.
problem because as
Yeah.
far as in my knowledge, only this parameter is getting changed, so we can calculate the other things. Because the Henderson-Hasselbalch equation is also derived from here only, from this
Right.
particular equation only. If we do some modification and uh, change, because instead of writing k, if we write in terms of log or pk, the Henderson-Hasselbalch equation will ultimately form. Okay, but
Okay.
that is true because based on pH only, the concentration of HOCl and OCl will govern. because
Yes, sir.
under pH of 5 to 7, the HOCl will be active, and above that, OCl will be more predominant. Okay,
Yes, sir.
so maybe there is something more to this problem. I will see what he has discussed, and maybe we can discuss. But uh, for this problem, you can, for now, you can simply solve using this equation. Okay, so this is
Sure,
also
sir.
correct. Okay, yeah, thank you for letting me know. I will check that.
Thank you, sir.
Yeah. So yes, this is the answer. Similar thing. So OCl minus, we can get it. Okay, the last question for today. So actually, this is not there in your syllabus, but some idea I will give you. This mostly it won't be asked. So it is actually calculating how much of phosphorus we can remove. Okay, in the filtrate, we have to calculate how much is P is there and how much P is there in the treated effluent. So basically, what happens is the phosphorus accumulating bacteria have some capability to take phosphorus, and some other heterogeneous bacteria will also have some capability to take the phosphorus. Okay, so you can see the P content in P accumulated bacteria is 0.3 gram of phosphorus per gram VSS, whereas the P content of other bacteria is 0.02. So there is a vast difference, almost a difference of around 6 times, 7 times difference is there. Oh, not even 6, 15 times difference is there. Okay, so that's why the amount of phosphorus that can be taken up by the phosphorus accumulating bacteria is much more than the other bacteria. So we can make a small calculation based on it. So I am not going through the calculation, just to give an idea, and also the amount of PAB, or the that polyhydroxybutyrate or alkylinoid that can be formed, is based on how much organic matter is present. Okay, how much readily available organic matter is given. So based on the COD value, we will find out what is the actual COD, then how much of this is biodegradable. So you can see COD is 300 milligram per liter, but out of it, on the biodegradable COD is 200 milligram per liter, and BSCOD is nothing but biodegradable soluble COD. So that is the readily taken COD. So that is only 50 milligram per liter. Okay, so corresponding to that value only we can form the PAB. So these are the few things which you may learn in your higher studies, but for now it is not required. Just to give a context of what kind of problems we can solve in this phosphorus accumulating bacteria, I have just shown this problem. Okay, and then the yield and the decay constant, the BSRT, all those things will be given. So let's not go about into all these things, because it is not for your exam point of view, but just as a general knowledge, I have shown it. If any of you wants to further solve or get to know more about this problem, you can mail me. I will send you the solution, and maybe we can discuss in the next class if you want. So, but for now, I am just skipping it. So yeah, so that's all from my side for today. We'll meet again next week on 10th March, same time, 7 to 9 p.m. And if you have any queries, you can reach out to me. So yeah, if you don't have any more questions, you can leave the session. Okay, that's all from my side. Thank you.